Have you ever really stopped to think about what's going on behind the scenes when you're just, browsing the web? We do it 100 times a day, but that simple act is one of the most complex coordinated dances in the modern world. Okay, let's dive in and unpack how the internet actually works. So, it all starts with a single click. You see a link you want to check out, you click it, and boom, like magic, the web page is right there on your screen. It feels instantaneous, totally seamless. But is it really that simple? Well, not quite. You see, in that split second, the request from your computer is setting off on this wild adventure. It's traveling through a whole maze of hardware and software, zipping across town, maybe even flying across oceans, all just to find one specific server and bring back the info you asked for. It's an absolutely incredible journey, for sure. Now, to follow this journey, we're going to need a map. And in the world of networking, that map is called the OSI model. I know, it looks a little technical, but don't worry. Just think of it as a 7-step process, kind of like a recipe. We're going to walk through the most important parts of this process using some really simple analogies, starting right at the top. Okay, our first stop on this OSI map is what we'll call the mailroom. This is where it all begins. Before your request can even think about going anywhere, it needs to be properly written, packaged up, and basically prepped for its long trip across the digital world. So that click you made, it instantly generates a request written in a very special language. This is HTTP, which stands for Hypertext Transfer Protocol. You can think of it as the actual letter you're sending. It says something like, "Hey, web server, I'd really like you to send me the contents of this specific page, please." All right, next, your letter goes down to the transport layer. And this is like the postal service deciding how it's going to send your mail. It's got two main options. There's TCP, which is like sending something via registered mail, super reliable, it checks to make sure every single piece arrives safe and sound. Or there's UDP, which is more like a standard postcard. It's fast, but there are no guarantees. For something like a web page, we almost always use the reliable one, TCP. So how exactly does TCP guarantee that reliability? Well, it's all thanks to something called the TCP header. Inside this header, there are these little fields for a sequence number and an acknowledgement number. This basically works like a numbering system for all your little data packets, letting the computer on the other end reassemble them in the correct order and confirm that, yep, every single piece has arrived. It's a pretty brilliant system for making sure you get the full, complete web page and not a jumbled mess. And here's another thing. The internet doesn't just send your request in one giant chunk. It uses something called packet switching. The old telephone system, that used something called circuit switching, where it would create a single, dedicated line just for your call. The internet is way smarter. It breaks your data into all these little packets, or you could think of them as envelopes, and it sends each one on its own. And that matters because it makes the whole network incredibly resilient. If one path gets clogged up or fails, the packets can just be rerouted on the fly. So our data is all packaged up, but how does it know where to go? Well, that brings us to our next big step, the digital postal service, whose entire job is to figure out the right address. Every single device connected to the internet, your phone, your laptop, a massive web server, everything has its own unique address. This is its IP address, which stands for Internet Protocol. It works just like a street address, telling the network exactly where to deliver your little data packets. This whole addressing system is handled by what's called the network layer of our OSI map. Now, that's simple enough when you're talking about one device. But what about a huge organization, like a bank? They might have thousands of computers, ATMs, servers, you name it. Giving every single one a unique public address would be super wasteful and, honestly, a management nightmare. So, how do they deal with that? Just imagine a bank, right? The finance department needs 30 IP addresses for its computers. Customer care needs about 24. And the ATMs, well, they definitely need their own secure network. You can't just throw them all onto one giant, messy network. They need to be separate. They need to be secure. But they all have to work under the bank's single public internet connection. The solution here is a really clever process called subnetting. This lets a network administrator take one big block of addresses and just chop it up into smaller, way more efficient subnetworks. So now, each department can get its own private network perfectly sized for exactly what it needs. And the result is a system that's just so much more efficient. Instead of trying to assign addresses from one massive, unwieldy block, you can create a perfectly sized little subnetwork for each group. This carves out just enough addresses for everybody, which cuts down on waste and massively improves both organization and security. Okay, so our packet now has its address, it's packaged up, and it is ready to go. The next step is to actually hit the road, to get onto the physical and local infrastructure that's going to carry our data from point A to point B. But wait, before it hits the physical wires, our little IP packet gets placed inside one last container, a data frame. This happens at the data link layer, and you can think of it like the standardized shipping container used for local travel. It has its own local addresses to get it safely to the next router on its journey. So what do these local roads even look like? Well, they can be laid out in a few different ways, which we call topologies. You might have a star layout, where everything connects to a central hub, kind of like spokes on a wheel. Or you could have a ring, where each device is connected to the next one in a big loop. This layout is what determines the exact path your data takes on its very first and its very last mile. Now, just like a real highway, the digital highway can get pretty jammed. When too many people are sending too much data all at once, you get congestion. Packets get delayed, sometimes they even get dropped completely. So how does the internet manage all this traffic? One really popular way to manage this is the token bucket algorithm, and the concept is actually pretty simple. Imagine a bucket that's being filled up with tokens at a steady rate. To send a packet of data, you have to reach in and grab a token from the bucket. If the bucket's empty, you have to wait for a new token to show up. It's a really elegant way to smooth out those crazy traffic bursts and prevent the whole network from getting overwhelmed. All right, our data is packaged, it's addressed, and it's on its way. But this whole journey is happening out in the open. So the final and maybe the most important piece of this whole puzzle is security. This applies across a whole bunch of layers on our map. How do we keep all this information safe from prying eyes? Well, the primary tool in the toolbox is encryption. And there are two main flavors. You've got symmetric encryption, which uses one shared secret key to both lock and unlock the data. It's super fast. Then you have asymmetric, which uses a pair of keys, a public key to lock it and a private key to unlock it. It's a bit slower, but it's incredibly useful for sharing those secret keys securely in the first place. Let's look at a classic example, the RSA algorithm. So imagine Alice wants to send a secret message to Bob. She finds Bob's public key, which is out there for everyone to see, and she uses it to lock the message. Now here's the magic part. Once that message is locked with the public key, the only thing in the entire world that can unlock it is Bob's corresponding private key, which, of course, he keeps completely secret. And finally, we have the network's first line of defense, the firewall. A firewall is basically like a security guard standing at the gateway of a network. It inspects every single packet trying to come in or go out, and it decides, based on a set of rules, whether to let it pass or block it. It's an absolutely essential tool for protecting a private network from the wild west of the public internet. So there you have it. From a simple click to a request that gets packaged in layers, addressed, sent through congested highways, and protected by encryption and firewalls, that is the incredible journey your data takes. These protocols and rules, they were built over decades to create the internet we all know and use today, which really makes you wonder, what new rules and protocols are going to shape the internet of tomorrow?